Okay, so welcome to, I guess it's, lecture 21. So, so I want to just start off today just by addressing a few things. So, last time I presented a theorem to the effect that if you have an operator, so what was the proposition? If we have a Dirac bundle over M, G Dirac bundle, and the associated Dirac operator, so we talked about when we can decompose. So the question was when can we decompose D into this cylindrical shape, or into this into this canonical form of dt plus a near the boundary, right? So last time I just said that the metric G is dt plus G M near the boundary, but actually we also need an additional condition, okay? And you can see that actually in the computation. And the additional condition is that if we have, so what we really require is if we consider a basis, so if we have S J T X, so this in particular means that near the boundary we have, so the measure splits up in a nice way, right? But in particular, if this is a basis, if this is an orthonormal frame near the boundary, near the boundary, then we have to have a certain, in the calculation, we have to end up calculating this quantity here. And we really have to do this regardless of the kind of connection that we choose, right? So regardless of the kind of choice of orthonormal frame. And what we really need is we need the orthonormal frame to be 0, so it needs to be constant along the direction of t. Okay, so we need to be able to decompose the operator in this way. So there's a missing condition like this that makes the whole thing work. So the point was that actually if you have this form for the metric only, then if you're working on something like the Hodge-Dirac operator, that's enough. Because you can see that if you, so the point is that if you now identify the bundle on the manifold near the boundary by parallel transporting along T lines to the boundary, so we can associate, so always we can do this, right? So always by parallel transport, we can write a section, say U in E restricted to this neighborhood UR, I'll write phi, as phi equals phi of Tx. Now we get EI of, phi I, EI, well, E was probably a bad choice for, okay, so where EIX is an orthonormal frame on E restricted to the boundary. Okay, so we can always write it in this way. And so then the question is, how does this change the connection in this identification? And then what we really need is if we write, so now I've screwed myself because I've written EI here. So let me write S here and SI for the frame. So if EI is an orthonormal frame for TM and E1 is DT, then we need that the DT direction of the EJ X is 0. Okay, so things really need to be flat in the cylindrical direction. This is what it really means. And we have that, of course, if we're on, say, the exterior algebra, because the connection that we have induced from the Levi-Civita connection, if the metric is product, will also have this nice property. Okay, that's all I want to say. So, all right, and anyway, this is now included in an exercise to try and compute this more precisely. So, yeah, last time we also started talking about invariant polynomials and constructing these even form, even form valued objects from these polynomial maps. So what did we have? We had P, which is a polynomial map if it takes us from matrices into the complex numbers satisfying P T X, T inverse T is equal to P of X for all invertible T, right? So this is what we had, and then we had a way of then constructing P of omega, where as a even form, where omega is what? This is just going to be inside a frame. This is just equal to this is the curvature 2 form, right? So is the curvature 2 form, which meant that Ji is actually a 2 form, right? So of course we have to write this. This is a local expression, but the point was that if we now have this invariance property, taking lambda tilde ij of P is equal to lambda of ij under a change of bases. Okay, so we get a well-defined object P of omega on the entire manifold. So this is going to be C infinity M valued in the even forms now, right? And the example that we had, of course, was the determinant. Okay. Now let's move on to constructing a very important class of forms. So definition. Let P be an invariant polynomial map, an invariant polynomial map of degree k. Okay, so that's important. And omega, a curvature 2 form. So arising from some connection. Then the form that we get now, it's not just, I mean, it's more than just being in the even algebra, in the even forms. It's actually a 2k form now, and this is called the Chern-Weil form of omega via p. So, of course, we also talked last time about the DRAM cohomology, which is for, you know, the kernel of the differential operator, the kernel of the exterior derivative acting on k forms mod out the image of the exterior derivative acting on k minus 1 forms. So, of course, this now also identifies a class, so we can consider this, and then here, of course, the point is that this, in fact, is now independent of the. Okay, so I'll make a remark. So this is H2K DRAM M2K forms is the Chern-Weil class. Okay, so this is the associated Chern-Weil class. Now, I just want to make a quick remark. This class is actually independent of the 2 form. The curvature 2 form, right? So actually this is this is actually really a topological object, and often P omega is simply written as P of E, right? So E is the vector bundle that we're on. So it's really a property of the bundle and not really of the connection. Okay, but of course the 2 form certainly depends on the choice of connection. Okay. So, sorry, the P of the 2 form, the P of omega, P of the curvature 2 form. All right. So now for the polynomial map P of A, defined to be the determinant of I plus I on 1 on 2 pi I of A, let C of omega be P of omega. Maybe actually I should have called this C of A, right? So C of A is the total. So this is really a definition, actually, right? So this is an important definition. So this is the Chern form or class. Is the total Chern form, and CE equals C omega, which is now in the even cohomology, is the class. Okay. So note, so maybe another remark, note that C of omega is equal to 1 plus C1 of omega plus Cn of omega, where Ci of omega is now in is a 2, well, k, is a 2k form. Okay. All right. So what happens at the level of the dual bundle? So in what is to come, we need to understand what happens at the level of the dual bundle, right? So let omega be connection to form, and nabla and omega star the to form corresponding to the induced connection that takes us from E star to the dual bundle, satisfying phi star psi. So this is just the exterior derivative, right? So this is the exterior derivative in the direction x. So this is a function, and we want it to be equal to, we want the product rule star phi star of psi plus phi star acting on nabla x psi. Then we have that ck of omega star is equal to -1 to the power of k ck of omega. Okay. Okay. Another fact. So this is fairly straightforward to compute. Okay. So you can expand everything out. I mean, it's just really a point-wise calculation, right? Locally, you just write it out in a well, I'll leave it as an exercise. But the way you do it is you expand everything out locally, and then you use this condition to understand how the coefficients of the omega star relate to the coefficients of the omega, and then it just pops out. Another lemma is what happens when we have a compatible connection, right? So we're not going to be just dealing with just general connections because that's limited in what we can do. So typically in applications, we're going to at least have a connection and a metric that are compatible with each other. So if nabla and H is a compatible connection, and metric on E, then C omega is real valued. Actually, it's a lot more than that. It has so-called integer periods. So when we integrate against it in some meaningful way, we get integers. But we won't get into that. That's a lot harder. The reality of it comes out quite easily. So what's the proof? So by compatibility, so compatibility implies that if we write this out in an orthonormal frame, so this is expanded now in an orthonormal frame, it's skew Hermitian. Where we have written this in an orthonormal frame. Okay, therefore, so we look at C omega and its complex conjugate. So remember, this is just a, yes? Yes. Yes. That's right. And you will see this, right? You will see this pop up. So we have, this is 1 plus 1 on 2 pi I omega. And so what happens now, so this we absorb into the determinant, right? So this is going to be 1 minus 1 on 2 pi I, the conjugation of the omega. Now the determinant preserves the transpose. So let's put a transpose in there. Okay, so this is going to be det 1 minus 1 on 2 pi I transpose. So maybe we wrote TR before, I can't remember how we wrote it. And what is this? So this is exactly now going to be the determinant on 1 minus 1 on 2 pi I of the adjoint. So this is the skew adjoint condition. Sorry, this is exactly the adjoint of it. And then the skew adjoint condition means that this is going to be back to 1 on 2 pi I of omega. So again, when I'm writing omega here, I'm really writing it out in an orthonormal frame, right? So just, I mean, of course, it's okay to do this. It's abusive notation because we have a global object, but I mean, it's important to keep in mind that this is really a local computation. And what is this? Well, this is exactly equal to C omega. Okay, so this shows that it's real. Okay, so with that in mind, we want to now move on. So what is the end goal? What I want to do is to use all of this to try and describe a very geometric application to spin Dirac to the spin Dirac operator and also another operator called the signature operator of the Atiyah-Patodisian index theorem. So we have to somehow understand how all of this works now. So everything up to this point has been in the context of complex bundles, right? We've done everything with complex connections, complex bundles, and so on and so forth. So let's try not. That's the skew adjoint condition, right? That's the skew Hermitian condition. Yes. Okay, so what we want to talk about are real bundles, right? So with real bundles, we have an additional gadget called the Pointryagin form and the Pointryagin class, which we can discuss. So real bundles, Pointryagin, Pointryagin. You can see I'm slightly dyslexic. Forms and classes. Okay, so now for our purposes, let V be a real bundle. And let's let E be the complexification of this, right? So we complexify this real bundle. So now we have this very important lemma. So if omega is the curvature 2 form, so okay, let me not start like this. Let H, or nabla H, be a metric compatible, metric and connection on V. Okay, so now it's real. Okay, so these are real objects now. And let nabla C and HC denote the canonical extension to V tensor C. Then for the induced two form omega C, we have the following. CK of the complexified two form is CK of the adjoint two form. And then from the lemma before, we have, let me just leave it as this, okay? All right, so why do we have this? So this occurs since omega is real, omega is C is real, and hence skew symmetric. Not just skew Hermitian, right? It's skew symmetric. Therefore, nabla C star, therefore nabla C, all right, therefore nabla C star, nabla C is also skew symmetric. Okay, so before we had that for a general complex connection, we don't have this, right? It's going to be skew Hermitian, but here we have that it's skew symmetric. And then this statement follows, right? Then direct calculation yields the statement. But something very important happens now, right? So let's write a corollary of this. For nabla H as in the lemma, CK of omega C is 0 if K is odd. So what is the proof of this? So we've already seen that due to the skew symmetry, we have that CK of omega C and CK of omega C star are equal. But we have something more happening now, right? We have that from previous lemma, CK of omega C star for a general complex connection, so this is a particular complex connection, is equal to -1 to the K CK of omega C. Therefore, we have CK of omega C is equal to CK of omega C star is equal to -1 K CK of omega C, and this can only be satisfied if K is even. And this can only be satisfied if CK omega C is 0 for K odd. If CK omega C is 0 for K odd. Good. Okay, sorry. So now with this we can define the following, right? Pontryagin forms and classes. Okay, for V nabla H M real vector bundle with the metric and connection compatible define pk of omega equals to -1 to the power of k c2k of the complexified form, which, so we already know, I mean, even for a complex connection, we know that the Chern-Weil, or the Chern-Weil class lands us in the real in the real forms, right? Real valued forms. So this is going to take us from M to so this is going to be a form that's going to land us in 4k of M with real values. And the total Pontryagin form to be P of omega equal to 1 plus P1 plus, okay, so this is now going to be in M with the 4-dimensional in the four in form in they're going to be differential forms of which are of multiple 4k forms. Okay. Similarly, we have the Pontryagin class, which is going to be in the 4k DRAM with real values, and P of V is going to be in the object 4 star DRAM and R. Okay, good. So now the Pontryagin forms are really going to be the crucial objects for us. That's going to connect the index theorem to geometric quantities. Okay, so let's think about how to take certain it's like a functional calculus. So we want to really take we want to apply functions to these Pontryagin forms. Okay, so let f of x equals to f naught plus f1 x1 plus f2 x squared plus so let this be the formal power series, or a formal power series. Then we define the map capital lambda of f, taking us from the from m sections of the even forms back into sections of the even forms by the restriction of this onto the k plus 1 forms oh sorry, how did I do this? I have to really check the numerology here. So it should be the 2k forms over m is going to be something like minus 1 to the k plus 1k f j id on 2k forms. I might have gotten this a little wrong. I'm sorry, I have to just, yeah, let me these exact exponents I have to really check. I think it's correct, but anyway, it's not so important. I'll have these corrected in the lecture notes. Okay. So anyway, so recall, for instance, so recall that, so why do we care about doing this? Log of 1 plus t we can expand as t minus t squared on 2 plus t cubed on 3 minus dot dot dot. Okay, so for a fixed degree form, so only finitely many terms occur in the expansion, right? Because when we do this, we're going to eventually terminate. So let's just look at what log of p omega looks like. So this is going to be log of 1 plus p1 omega plus p2 omega plus dot dot dot. And so by the above definition, what we have, it's not from the above definition. This is a way of defining the logarithm. So what we get is p1 of omega plus p2 of omega minus p1 omega squared on 2 plus, and so on and so forth. Okay, so this is what we end up getting. And now we define the following important object. So again, so for f of x being a formal power series, f1 of x, f1 x, f2 x squared, formal power series, we define pf of omega as taking the exponential now of logarithm of f applied to the log of p omega as we've just written it out. So the exponential is defined in a similar way by a power series expansion, and this is going to land us now in the forms for star. And this is called the multiplicative characteristic form. Okay, so I'm sorry, I know that this is all a bit abstract and hair-raising, but it does have a purpose. The essence of all of this really is the fact that we're sitting inside a commutative algebra, right? So this construction can really be repeated in any commutative algebra. So you could do this construction, for instance, also in the D-Rhine cohomology. But we don't want that. We want to really stick with forms for the reason that I said last time. So at the level of a closed manifold, it makes sense to talk about classes because there is no boundary. So the image term, the error term that one gets in the DRAM cohomology, this always integrates to 0. Whereas that doesn't happen in the situation of boundary, and so then we have to be careful and we have to use specific forms in order to move forwards. Okay, so with all of this in mind, so I mean it's not so important that you connect with this straight away. I'm actually really just saying it because it really needs to be said. It's sitting at the heart of what we're about to talk about now. But the important thing is that there is a construction, there is a way of taking a formal power series and then constructing something from the Pontryagin forms from the formal power series, and then we have this so-called multiplicative characteristic form, which is the object that arises in geometry for specific choices of f. Okay, so now let's move on and think about some geometric applications. In even dimensions. Okay, so throughout, well, from now on, unless otherwise stated, we assume that mg is compact with dimension n equals to 2m. So okay, so it's clear. So clearly, the dimension of the boundary now is, well, 2m minus 1. And we continue to assume that G is product in a neighborhood of the boundary. So the spin case. So the first subsection is the spin case. So suppose further that M is spin, i.e. admits a spin structure. So in particular, recall that in particular M is orientable. Okay, so it's a necessary condition for spin manifolds to be orientable. So because we're in even dimensions, we have, so in this case, we have two non-trivial and canonical irreducible representations. So what I mean, you can really write this out concretely, right? So these are inside some chart or inside some frame. This is of course going to be given by the irreducible representations, i.e. the polymatrices that you have in Rn, and the way that the spin bundle is put together is you know, you have a choice of spin structure and metric. So the metric gives you the orthonormal frames. You have a spin structure, and then you have some sort of computation, or you have to do some sort of a matching game in the check cohomology to know that this bundle is well defined, right? But let's not really get into that. We'll just take it for granted, so we'll call them rho plus minus. So then in particular, then the spin bundle splits into two bundles. So we have the positive spinners and the negative spinners. Okay, the positive and negative half spinners. Okay. So, I mean, what is the dimension of the full so recall that the dimension, because we're even dimensional, we have that the dimension of the spin bundle is equal to 2 to the n on 2 or 2 to the m. And what we have for these two subspaces, they're of equal dimension, so it's really splits this bundle. So the dimension of plus minus m is exactly equal to 2n minus 2 on 2, which is what? So this is going to be equal to 2 to the m minus 1. Okay. So with respect to this splitting, so in particular it means we have some projectors here, so the Dirac operator also splits, right? The Dirac operator, the spin Dirac operator, can be written as d equals to d plus d minus. Maybe I'll slash them all. So d plus minus is going to map us from what? It's going to map us from positive spinners to negative spinners. That's not how it's going to work. It's going to be plus minus to minus plus, right? Oops. Okay. All right. And from our considerations before, we have that d is equal to some sigma naught dt plus a near, I'll slash the a, near the boundary, and we have that a actually is a matrix of this form, a plus, a minus, so those are the, so it's actually a diagonal matrix. It's really this symbol omega which flips things, right? And d plus now is the object we're interested in, so this is going to be omega plus dt plus a plus. Okay, so that's the object that we're going to look at. Okay, so now here's the lemma. So the positive spin bundle restricted to the boundary can be identified with the spin bundle on the boundary itself. Okay? And the A with the spin Dirac operator on M. Okay, so we're almost there. We're almost there where we want it to be, where we want to be. So now let me define a polynomial. The A hat polynomial which is the square root of x on 2 divided by shin square root x on 2. So this has this following expansion, some interesting numerology. And the logarithm of this is as follows, as a formal expansion, right? 2880 plus ... Now we define the A, so the A hat of omega is P of this A hat of omega, which was what? Which was exp lambda log A hat acting on log of P omega, which we said was a, well, I won't write it there, and in fact we can give a small expansion here, so P1 of omega on 24 plus 7 P1 omega squared minus 4 P2 omega on 5760 plus ... right? So okay, so this, the square here, I should really say when I'm squaring, I'm really talking about the wedge product, okay? And this is really where the fact that it's an even algebra, it's a commutative algebra really comes in. So I can replace the product with just the usual product because it's a commutative algebra. Okay, so why are we doing all of this? So now let me at least give you a theorem. So Mg is Riemannian spin manifold with boundary of dimension n equals to 2m, okay? And G is product. G is equal to dt squared plus G near the boundary. Then, so I have all of the hypotheses that I want. Okay, good. Then this integral, so remember in the APS theorem we had this alpha naught x d mu g over x term, so that's what this will be. This is the integral now of a hat of this omega over m, and therefore, well, and the index of d plus APS is equal to the integral over this a hat of omega minus the dimension of the kernel of this a hat plus the a plus hat at 0 divided by 2. Okay, so this is why we worked so hard to talk about all of these forms and taking polynomials of these forms and so on and so forth. Okay, so a couple of remarks I want to make. So the first remark is the integral a hat of omega should be understood as picking out the top order form. Okay, so, I mean, of course, it doesn't make sense otherwise, right? this is a differential form that has, I mean, it lives in this 4-star algebra, so we have to really pick out the form that is at the top. So that's the first remark. The second remark I want to make is compare this with the Atiyah-Singer index theorem. So there we have, so this is M boundaryless, so M, maybe I'll call it M prime G closed, boundaryless, with dm prime is 0. And then there the index theorem reads that the index of, so there's only one operator now, right? Because it's I mean, it's a closed manifold, so there's unique extension. So this is equal to the integral over now a hat of a hat of Tm, where a hat of Tm is the actual class that this thing lives in. So the point is that so i.e. without boundary, this reads analytic index equals topological index. Okay, so it really doesn't matter about the connection that one chooses here. Whereas for us, we really do care about the connection that we're integrating against, because we have boundary. So that's a very important, in our situation, we have analytic index. Yes. Well, you cannot integrate. How do you integrate a n-1 form on M? Doesn't really make sense, right? Yes. So it is a definition. Okay, so for us, what happens is we read that analytic index is equal to a geometric integral plus boundary contribution. Right? So the index theorem is somewhat, I mean, boundary really changes the nature of the index theorem in some sense, right? Okay. Let me now also give you something that is a little bit more general now, now that we've highlighted this. So something a little bit more general. So let E nabla H be a Hermitian bundle and so with nabla H compatible, and we also need it to be constant in the normal direction in a neighborhood of M. So this is of the boundary, right? This is again what guarantees that we have this cylindrical format for the operator. Then for the induced Dirac operator, the twisted Dirac operator, the twisted spin Dirac operator, dE on this twisted bundle, we have, so again we have an index theorem. So the index theorem now reads that, so this is again a direct consequence from the APS theorem that we've proved. So that D plus E APS is equal to now the integral over M of the Chern form. So the turtle, we have to take the total Chern form and wedge it with the A hat. Minus dim K A plus E. Oh, okay. Move this to this line. Plus eta A plus E at 0 on 2. So this is also why, so as a definition, we took that this integral is going to be on the top forms. Because in this format, it's very nice, right? I mean, when we take the wedge product of the Chern and the A hat, things might mix around, but then in the integrand, we just pick out the nth order term. Okay, so let's now discuss some of the geometric consequences of this. So let me first give an exercise. So the twisted Dirac operator dE decomposes into dE plus, dE minus, so I should say the twisted bundle splits, twisted bundle splits M tensor E into plus M tensor E and this holds and that. Okay, so we want to now think about some geometric consequences, right? So so vanishing A hat and consequences. So let's think about what happens when M. So okay, so we always so let's just remember that we have n is equal to 2m. So let's think about the case that m is odd. Okay, i.e. n is equal to some 2k plus 1, which is equal to 4k plus 2, and that's going to be congruent to 2 mod 4. So what happens then? So we pick out now the top dimensional form, and that top dimensional form is going to be 4k plus 2. So, okay, so if we look at 4k plus 2, this is certainly not going to be in the 4-star algebra, right? So then that means that A hat of n of omega is 0 in this situation. Okay, so the index theorem then just says that the index of the operator is purely given in terms of the boundary contribution. Okay. Let's think about now, so there are two more cases left. So let's think about the case that m is congruent to 1 mod 4. So this happens if and only if m is equal to 4k plus 1. So that's if and only if n is equal to 8k plus 2. So the dimension now of the boundary is what? So this is going to be n minus 1, which is going to be 8k plus 1. So now we have to really use the fact that a plus can be identified with the Dirac operator on the boundary, right? Recalling that a plus can be identified with the spin Dirac up on the boundary, we know, so this is of course nothing we proved, but this is already something that's known, that this spin Dirac operator is equal to some I times B, where B is real skew adjoint. And actually that's enough to guarantee that the spectrum of the A plus is symmetric, and actually that forces the eta invariant to vanish. So okay, so in this situation, right. Okay, so in this situation, again, we have what? So also, we have that the A hat, the top level form, is going to be A hat of 8k plus 2 of omega. And as before, this is no longer in the 4-star algebra, right? So this is going to be 0, which means now, so how does the index theorem read? This means that the dimension of the kernel of this A plus is precisely equal to minus the dimension of the, it's going to be minus 2 index of D plus APS. Okay. So actually, we have to use another fact now, coming from other considerations, that the dimension of the kernel of A plus mod 2 is an invariant on the boundary. And so that means that the dimension of the kernel of A plus mod 2 is congruent to 0, right? So it vanishes. For spin boundary, right? Okay. So it reveals quite a lot of, the index theorem really reveals a lot of rich structure, right? So that's really the take-home message. So we have one more case left, and that case is the situation of M being congruent to 3 mod 4. So if it's 3 mod 4, then this occurs if and only if M is equal to 4k plus 3, which means that n is equal to 8k plus 6. So again, the A hat genus is going to vanish, right? So the A hat form is going to vanish. And so, okay, so it's going to vanish, so that's the first thing. Another thing that we have is a fact that in this particular dimension, the spin bundle has a quaternionic structure. Oops. Structure Q, such that Q of A plus is equal to negative, so it anti-commutes with the Q. So that actually then, as we've seen before, I mean, when we considered the situation of the symbol dt having this anti-commuting relation, but actually any anti-commutator is okay, right? If you really have any anti-commutator in this way for the operator A plus, then we can deduce from the same argument that the spectrum of A plus is symmetric. And okay, whenever I'm saying this, I'm saying this including multiplicities, right? Counting multiplicities. So that we've seen forces the eta invariant, or the eta function, to be 0, and then we get that the index is satisfies this, as we've seen before. And what does that mean? So that tells us now in this situation that the dimension of the kernel of this A plus is even dimensional. Okay, so the point is that we end up being able to extract quite a lot of interesting information. So this is just a small sample of the applications. I mean, if you go out in the literature, you'll see dozens of interesting applications for the index theorem. Unfortunately, I mean, even to try and describe this, we have to take a lot of facts for granted, and that's the primary reason that I didn't really start giving out more applications than this. But it just goes to show that actually we can extract out a lot of information about dimensionality of kernels, or topological information, or geometric information from on spin manifolds with the aid of the index theorem. Okay, and in some sense this is also the purpose of proving such an index theorem, because this is also true in the situation of the index theorem in the boundaryless case. There again, you get a lot of important and rich information once you start to play around with the index theorem for these specific operators.